I am Ritwika Mukhopadhyay from the Swedish University of Agricultural Sciences, Sweden. I'm a PhD candidate there, and I'm working on modeling of forest above ground biomass, combining field inventory data and LiDAR data as an auxiliary data. So I'll give an introduction how the data is collected. So the remote sensing data that I'm using is from an airborne platform, and these are in the form of 3D point clouds. And from the pulse that is sent from the sensors and what we receive back from the ground or the vegetation, we calculate the height percentiles, which I'm using as the predictor variables in my models. So we can calculate the cumulative height graphs from these first return, second return, and the last return. And then we divide the cumulative heights into like 10 quantiles and then calculate the first, not first, but 10, 20, 30, 40 height percentiles with some thresholds. And what I'm focusing on is the biomass, which can be divided into two parts, the above ground and the below ground. So it is important to estimate biomass because it helps in the computation of the carbon content in the forest, which helps us in analysis of climate change mitigation. And I mostly focus on only the above ground, not the below ground. So this is how the point cloud looks like. This is super blur image. Yeah. And this is my study area in Sweden, where I took a sub area for this present case study for this course. And these are the field inventory data collected by the Swedish National Forest Inventory, the Swedish NFI. And we also have the LiDAR metrics for these cluster sample plots, but I'm only using this, the green square here, only this area for easier computation. Okay. So is it okay? Okay. So I have tried to compare the efficiency of three models: the random forest regression, the support vector machine for regression, and the feed-forward neural network for prediction of forest biomass. And after loading the data, this was the distribution of my response variable, which is the field biomass. And there were a lot of zero biomass values, which I cleaned.
Sorry,
Yeah.
Can you go back to the table?
Yes.
Can you just go over like the features that you're using there?
This doesn't show all the features. Okay.
Like some of the most important.
Yeah, the total AGB is the response variable for my model. Then I use the longitude and the latitude. And the other height percentiles are not shown here, unfortunately.
So total AGB is what?
The target variable. The field biomass.
Biomass.
Yeah.
Okay.
And what is this number is like? What means 200 biomass?
Yeah, for the second observation, we can say it's 272 tons per hectare.
Can you get that from the library?
No, this is from the field.
Field work. Oh,
Yeah.
sorry.
And I had 217 field observations.
And for these rows that they are just zeros, for example, the row number 6, that means that that measurement goes back. Row number 6, you see that there are a bunch of zeros there?
Yes.
So you drop those?
Yeah.
Okay.
So after cleaning the data, it was a highly skewed distribution of my biomass. And these are the predictor variables. These are the longitude, latitude, the height percentiles up till 99. Then it's a vegetation ratio calculated based on the height percentiles. And these are the intensity metrics derived from the LiDAR data. So these were total 33 in numbers. So I used all of them for my modeling. And yeah, this is the overview of all the predictor variables. Then I
What are the different values for elevation of the data? So there is elevation of 10, 20. Yeah. There.
These peak.
Yeah. Let me see.
Okay, so when we calculate the cumulative height from the point clouds, we divide the plot into like 10 or 20 equal parts.
Yeah.
So 20 means like heights below the 20 quantile, we will discard all of it and consider only what is above it.
So this is the height of the laser
Yes.
sample.
Mhm.
Okay, it's not elevation.
No.
It's not altitude.
No,
Okay,
no, no.
okay. And this one is
These are the intensity, mostly the density of the point clouds in per square meter.
okay. So the density
Yeah.
So
that's basically some measurement of how high the airplane was from the measurement as well. Because if you're lower to the ground, the density is supposed to be higher, right?
No, the density is on the pulse density.
yeah.
That's right.
Yeah, these are the LiDAR footprints. So this, yeah, the
How
number
many?
of points is per square meter. That is the density.
All right.
Then I converted my the target variable biomass to fall between 0 to 1 with a normal distribution, and also normalize the predictor variables, all of them 33. And then I move forward with the random forest regression first. Here I used 25% test data. And there was a little bit of overestimation also. And then I tried to plot the importance, the feature importance, and I'll later come back to this plot again. Then it was the support vector machine for regression. Here it was very strange thing that I observed with the test size. The 50% was the optimum that I found. When I increased or decreased, the training score was going down and the test score was going high. So I stuck with the 50% and did not change it. And then I tried with the feed-forward neural network. I just modified the code provided by Antonio. Here it was 70% for the test data set.
70% of the samples part test data set?
Mhm.
So you're just training 30% of the data?
Yeah.
That sounds really great, right?
Yeah.
Did you check if 30% is enough to explain the variance of the data, please?
I didn't check it, but I just wanted to keep more for validation.
Wow, you want to do more for training, right? That's right.
Right.
Okay, we will change. No problem.
So
It's
here,
going to be fine, don't worry.
so the combination that I found for the hidden dimension range was 512 and the learning rate 0.01, which
So
was
what's the range of your output? Sorry,
0 to 1.
0 to 1.
That's why I used the sigmoid activation function.
But isn't the range of your outputs like the prediction of biomass?
Yeah.
Because it's normalized.
It's normalized, yeah.
Mm. And I increased the epochs later to 4,000 because it was not stabilizing anywhere. So I thought, or maybe if I increase it further more, it will improve.
But that one could be that you are doing the 0.0703.
Yeah, the test and the tree.
Also, yeah, and also sigmoid is not ideal there, right?
Mhm.
Do you agree with me?
Yes.
Why?
Yeah,
Why is not ideal?
because it can go up again. The epochs, right?
Sigmoid saturation is
Okay.
like 0, right? Like then you have a part sort of linear region, and then it saturates in 1,
Mhm.
correct? In your case, the saturation of the like near 0 and like near 1 makes no sense, right? Because actually what you're doing is sort of a regression, right?
Okay.
So like either you use rectifier linear unity because you don't want negative prediction either,
Yeah.
right?
Mhm.
Or you just remove activation altogether, right? And let the model try to map things in a linear way at all.
Okay. Then I computed the model statistics here, only the RMSE. And here also I tried to plot the feature importance. So now I can make,
And the
sorry?
feature important you calculate with, because this is a feature with Shapley.
Yes.
Shapley.
Yeah.
Yes.
Shapley. Okay.
Now if I compare the feature importance from the random forest and the feed-forward neural network, the sequence of the important features is reversed, I would say. And the PAT and the CRR is the two variables that I'm using for my own statistical model, which I don't find important enough in the random forest, but I was happy to see at least one of them important from the feed-forward neural network.
Yeah, I like this comparison, but I mean, they treated the variable in a different way, so it's normal.
I mean, like, what's the weight that you assign for that variable should be similar, right? If the variable is important, that should come through like this type of like feature importance analysis.
Very similar. So in the case of CR or the P8 that go quite okay, CR is quite down in both of them, but the P8 is huge different. What can we do?
So you see the bar, right? The bar in the plot of the random forest, that's standard deviation. Yeah, so like the standard deviation that was found by random forest is huge, right? I wish we could see also what's the standard deviation in the chat there. One thing that perhaps could happen is that, for example, you said that you use the P80, right? Do you have another variable that also is linear correlated to P80? Maybe like random forest finds these other variables that are linear dependent to P80 to be as informative as the P80, you know, like, and then just give priority to those.
It can be the P75, which is the first one there, is the most closest to P80.
Yeah, usually if they are in random forest, if they are very correlated, they stay close also in the variable important. This is what I read.
But also another thing I noticed was here it is giving the latitude and there it's giving the longitude.
So what was the speaking that you did for random forest?
It was
Did you training and test?
75-25, just the opposite, almost.
Yeah, so that one is
compare there.
you try to keep the same,
Yeah.
actually setting also the seed.
Mhm.
The seed, you know?
No,
Yeah.
actually,
You have it always in both, you use training and test in the same And then you can compare.
Yeah, I think that's going to be a better way to compare, right? And also, like both methods, they are trained in like stochastic fashion, right? So like the way how you learn how to assign weights to features and like, how the random forest create the trees and so on, it's done in a stochastic way. So like for you to be able to actually estimate if like those features are important or not, you should let the speed vary and run a couple of times so you can do statistics on that. And then you can see like, okay, out of like 10 training sessions, the PA turned out to be important, so like at least 8 out of 10. Then you can say, okay, PA is important.
Thank you for the feedback. So,
Okay.
yeah.
You have more?
Yes, a little bit more.
Yeah.
And this is my own model, which I am working on right now. I'm using the CRR and the PAT with the for a generalized linear model with gamma distribution. And so only these two rasters were available for mapping. And here I use the random forest regression for just to show a spatial mapping part.
The biomass.
Yeah, this is the biomass. And we can see here in around the water body, we have higher biomass. Thank you.
We know this story. We know this story. Okay, no, wait. So one point also, I also noticed that also, no, sorry. I think also the error can come from here. When you plot the, when you plot the response variable, yeah, so over here, ding, ding. So you have probably you have the 0 that Antonio was mentioned, and here you have the maybe the no data, another bigger value that is coming in the from this table over here. So the total GB, so probably that the 0 is the 0. So the cleaning operation, and the maximum can be another failing unless.
But you said to drop it, right?
Yeah, the 0 values I cleaned it.
Oh, maybe you need to clean 0.01. So yeah, be careful about this stuff, because then is completely skew, and you can gain immediately few percentage more. Yeah. And also the same for the maximum.
Ideally, this distribution will be like the right range, 0 and 1, right? That's the ideal scenario. So like if you have these gaps, like for example, the output of the neuronal network, once the output is moved, right? So once the output looks like a Gaussian distribution. So if you have these gaps, the outputs is still trying to fill up like that gap, like making predictions there, right? So like, and then when you compare the R square between the true values and the outputs, all the things that are between 0.8 and 0.9, they are all bad R square.
Yeah. And this one can be easily done after or even before that you normalize. You can do the statistic and you get the minimum, maximum, like who was doing, Chong, I think, or somebody else. So that one is the easy way to do it, and you can drop it if they come, especially if they come from satellite image or raster image, you spot immediately that some no data are big number that not be labeled as no data, because most of the time, many software, if your no data -999 in the GeoTIFF is labeled as no data, then Rasterio will read automatically, Grass will read automatically, and so on. But if it's not labeled correctly, then it's appearing the table, so it's really something that you have to pay attention. Okay, very good. Yeah, please.
When the light bounces back and do more bounces, does that mean that there is more biomass?
Yes. So if they,
I mean, it will only return once. It won't bounce back from the sensor. But for a single pulse, the number of returns we get, we calculate the profile based on that. But once it returns, it won't bounce back.
And is it a matter of time of the return of the light?
Yes.
Yeah, time, wavelength, and then it giving the height of the bump. So this, let's suppose that this one is bumping here, so it will return the value from here to here. Okay, so and if many points are bumping back, means that it's extremely dense. Okay, so it's very loose. Many points will go through, and you will have more. So the biomass is correlated to the amount of points that has been bumping back, you know.
What about the type of biomass in this case? Can you use the wavelength of the refracted LiDAR?
Usually with LiDAR, they don't do it type, so it's more a spectral signature from satellite image, so from image. Maybe the shape can tell something, because you know coniferous will bumping different than what the leaves. And sometimes also LiDAR winter and winter, yeah, broadleaf and coniferous winter, and so they can have different.
Yeah, it is.
Return.
Yeah, very different with leaf on and leaf off conditions.
So you can get some information about the type of species, but most of the time it's from satellite image. Oh, any more question? Okay, very good.